Hello and welcome back to Fourier Transform, the video series where we talk a lot about the special integral transformation and what we can do with it. And indeed, in today's part 29, we will see that we can transform a differentiation operator into a multiplication operator. I would say this is really important to remember. Applying the Fourier transform changes the one operator into the other. But as always, before we go into the details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a Patreon or Steady supporter, you can download a lot of additional material for the videos. And now the first thing I want to do in this video is to recall a calculation we have already done in part 26. There we just took a compactly supported smooth function f. And you already know the common notation for that is c infinity. Hence we don't have any problems considering a partial derivative and then applying the Fourier transform to this one. And then in the calculation we see that we have an integral with a partial derivative, which means that we can apply an integration by parts formula. And then, as you might remember, what we get out is I times the jth coordinate of p times the Fourier transform of f at p. And there you can immediately see that this is exactly the topic of today, because a differentiation gets transformed into a multiplication. However, now in contrast to part 26, we will formulate everything for Schwarz functions. So we just consider the bigger space of rapidly decreasing functions. And there it turns out that there is a more suitable notation for the operators involved here. For example, for the partial derivative with respect to the jth coordinate, we can just write del j. And on the other hand, we also need a good name for the multiplication operator when we multiply with the jth coordinate. And in the context of this video, let's keep it simple and just write capital M with index j. This means if we apply mj to a function g that is defined on Rn, then we could use any name for the independent variable, and let's say here we call it y. And then the result is simply yj times g of j. So this is the general multiplication operator that acts on functions, and in our case we would have I times mj. Okay, and now by using these short notations, we can formulate the differentiation theorem for the Fourier transform. In some sense, this is just the natural extension of the formula from above. This means now we just consider any rapidly decreasing function f. And then we actually get two similar looking results. And the first one, as already mentioned, is just the one from above. But now we can reformulate it such that we don't need names for the coordinates in Rn. So this is just the Fourier transform of the partial derivative of f with respect to the jth component. And now we know this one is I times mj of f hat. But obviously, as before, instead of f hat, we can just write Fourier transform of f. And the advantage of this formulation is now that we can immediately see what happens when we want to pull out this del operator. If you want to put it in front of the Fourier transform, it becomes this multiplication operator. And again, this is the thing you really should remember. The Fourier transform transforms differentiation into multiplication. And in fact, now in part B, we will see that this also works the other way around. In other words, now we want to know what happens when we want to push the differentiation del j into the Fourier transform. And now, maybe not so surprising, it simply becomes a multiplication operator minus imj. And here please note, if we wrote this formula with variable names, we would use xj for our multiplication operator. And on the other hand, we also would use the partial derivative with respect to pj here on the left hand side. Hence, you recognize that part B here also claims that the Fourier transform of f is differentiable again. Indeed, for just an integrable function f we would not have this property, but for Schwarz functions this always holds. So this is definitely something we should prove now in this video. However, let's start with part A, where we can almost copy the calculation from part 26. However, we have to change it a little bit because we cannot use the compact support from before. Hence, the integral for the Fourier transform actually has to go over the whole Rn. But since we know that this integral exists, we can actually approximate it by integrating over a ball. So let's say the ball has radius r, and then we just increase the radius more and more. So clearly in the limit r to infinity, we get out the same value for the integral. Hence, in order to calculate our Fourier transform, we can just concentrate on this integral on the right. And indeed, the advantage of integrating over a compact ball is that we can use the integration by parts formula. This one also works in Rn, and if you don't know that, please check out my multidimensional integration course. In any case, you might definitely know that we get two terms, and one is the boundary term, and the other one exchanges the place of the differentiation. This means in the second term here, which also has a minus sign in front, we have to calculate the derivative of this exponential function. Of course, this is quite easy, and the other factor is just the function f itself. And in addition to that, you should also know that on the boundary term we don't have the derivative at all, we just have the product of the two functions. And we also integrate here over the boundary of the ball, which is the n-1 dimensional sphere. Therefore we have the corresponding surface element d sigma involved. And another thing that also comes into this surface integral here is the normal unit vector that we just call n. And in fact, since only the partial derivative with xj is involved here, we also only have the jth component of this normal unit vector involved. So while this is the case, you can calculate by using the general formula, but for us it's not so important because we just want to estimate this boundary term anyway. And since n is a unit vector that is also normal to the sphere, it definitely has length 1. Therefore also any component in the absolute value is less than or equal to 1 as well. So now what we can do is to estimate this boundary term in the absolute value. So clearly we have the triangle inequality for the integral, so we can push the absolute value inside. And then we have the three parts here, where only one will remain. Clearly here we have the absolute value as equal to 1, and here less or equal 1. However, the middle part we can also estimate just by using the maximum of the function f that it has on the sphere. And to keep it simple, let's call this one f in the supremum norm on the boundary. And then the only thing that remains is the integral over the sphere, which means this is the generalized volume of the n-1 dimensional sphere. And at this point I guess that you know that for this there exists a nice formula. However, the good thing is that we don't need the explicit formula, we just need to know that inside the formula we have r to the power n-1. So we just need to know that the volume scales with this power of r. So we have a constant Cn that only depends on the dimension and then times r to the power n-1. So obviously the volume of the sphere increases when we increase r, but here on the left we also have something that rapidly decreases. In fact, the decay of f is faster than any polynomial, so this one definitely will cancel this factor here. And if you want to make it more precise, you could just use the formula from the last video. There we just said that we have a constant c and any power n here in the denominator. Therefore we could also take the dimension lowercase n there, and then the constant only depends on this n. And to avoid some confusion, let's call it cn tilde. And now since we work on the sphere here, this norm of x squared, which is the standard norm of x, is just equal to r squared. And that's already enough. Now you see that the power in the denominator is definitely higher than the power in the numerator. So I don't have to tell you more, when we send r to infinity, this whole thing goes to 0. In other words, this boundary term definitely vanishes in the limit process. Therefore only the second term remains, and that's easy to see that we just get minus ipj to the front. And there the minus sign just cancels, and we get exactly the result that we stated before. Namely, we find the Fourier transform of f here on the right hand side again, just with the multiplication operator in the front. And that's it. This is exactly the statement in part A, and now you know it also holds for Schwarz functions. And with that out of the way, we can immediately go to part B, which might be more interesting, because now we want to show that the Fourier transform of f is actually differentiable. More precisely, we want to show that this partial derivative here exists. And we can show that in a nice way if we just push the differentiation into the integral. Simply because inside the integral we don't have any problems, this exponential function here is definitely differentiable. And the common way to put it is to say that we want to differentiate under the integral sign. So we just have to justify this procedure, and we can do that by considering the derivative inside the integral. And this one is just minus I xj times the same exponential function and f again. So this is the important thing, and let's abbreviate this function by f tilde. And for this function we have two inputs, namely p and x. This is important for checking the requirements, which you can also look up in my multidimensional integration course. But I will state them here again because they are quite simple. First, we need that regardless which point x we fix, the function depending on p is a continuous one. This is quite clear because everything here is c infinity anyway, no matter which variable we consider. And the second requirement is that we have an integrable majorand. You know that because it's the common thing you need when you want to apply Lebesgue's dominated convergence theorem. And let's call the integrable majorand g, and this one should depend on the variable x, because this one is the variable we integrate over. But still, the inequality has to hold for any point p we can put in as well. And this is what we want, and g should be integrable, which means it lies in L1. So the only thing we have to do here is to define such a function g. And this is actually kind of easy, because we can just write down this absolute value. I and the exponential function don't matter, and what remains is just xj and f of x. And this one can already be our function g, because it's an integrable function. This is clear because f is rapidly decreasing, which means even after multiplying with xj, we still have a fast decay. And the reasoning is more or less the same as before. If this decay is fast enough, the integral cannot go to infinity. And I think this explanation is already good enough. If you want to justify it more, you can use a similar estimate to before. And now the result is that these two requirements are satisfied, which allows us to push the differentiation inside the integral. So then what we get is this integral where minus I xj is involved. And if we push this factor to the right hand side, then you see that we have the Fourier transform of this new function. And if we want, we can write this new function with the multiplication operator. And then we get what we expected from the beginning, namely the Fourier transform of this function at the point p. And there we have the general result. The differentiation goes into a multiplication operator. And after seeing the proof, this should not be mysterious anymore, because you see this just happens because we have our exponential function where such a factor comes to the front. But still, it's a very important property of the Fourier transform that we will definitely use in the future. So let's meet in the next video again, and I wish you a nice day. Bye bye.